Welcome again. Today we will discuss palladium catalysis, and palladium based reagents in organic synthesis, these are present in every lab and this is very useful for cross coupling reaction. So, if you see the periodic table, this is palladium is in the same group with nickel and it is the same row with ruthenium rhodium. So, palladium very useful for cross coupling reactions where CC bond formation happens. So, today's lecture we will first discuss Walker process, then we will discuss Fuji-Trost reaction and we will discuss different cross coupling reactions like Hague reaction we will discuss, Negishi coupling, Kumada coupling, then Sonogashira coupling we will discuss, Buchwald-Hartwig coupling which is amine formation, carbon-relative reaction with carbon monoxide that also we will discuss, and Segusa-Ito oxidation to generate enone from saturated ketone that we will discuss, and some coupling reactions like Suzuki coupling we already discussed earlier. So, we will not be discussed here. So, Walker process first we will discuss, and Walker is the name of a company. Walker oxidation of alkenes to aldehydes or ketones is one of the most important industrial processes developed by Walker Chemie in 1957. In this process, palladium catalyst is used in combination with oxygen and copper salt to transform alkenes to aldehydes or ketones. That we will see depending on the Markovnikov and anti-Markovnikov addition. In this reaction, copper 2 oxidizes the reduced palladium 0 to palladium 2 to regenerate the catalyst, while the reduced copper 1 is reoxidized to copper 2 by oxygen. The oxygen incorporated in the alkene to give the carbonyl compound is obtained from water. So, this is very important, the carbonyl group which is coming, that oxygen is coming from water. And this method has been applied to industrial synthesis of acetaldehyde and acetone. Suppose if you do reaction from ethylene, then you get acetaldehyde, and if you do reaction with propene, then you get acetone. So, this is the organic synthesis procedure, that if you react suppose 1 decene with palladium chloride 10 mole %, then copper chloride 1 equivalent, this is cuprous chloride 1 equivalent, then DMF water 7:1. So, water should be present and oxygen 1 atmosphere, 24 hours room temperature you get this ketone in 65 to 73% yield. This is the organic synthesis, the review, and another review also synthesis 1984 same year by Suji. So, what could be the mechanism for this reaction? So, alkene goes to ketone here with catalytic palladium chloride, copper chloride, oxygen, water, DMF, and the catalytic cycle will first involve the 2 Cl minus as to PdCl2. So, the more ligand will come, and now the ligand exchange will happen. So, the olefin will exchange with this Cl minus, 1 Cl minus will eliminate, and this coordination will happen, coordination of the olefin to the palladium, because olefin has electron cloud. Now, water will come, first water will do a displacement of Cl minus. So, again ligand exchange will happen and water will be here connected with palladium. And now, another molecule water will come and do an addition to this species. So, the rule will be by Markovnikov addition, and in this process you can see this OH is from the water, and in this process 1 H plus is eliminated, and this you see this attack happened to the most substituted carbon atom. After that, Cl minus will be dissociated from here to generate this neutral compound, and this is the rate determining step. And now, the elimination will happen. So, this elimination, this is the beta hydride elimination. beta hydride elimination. So, this hydride will be taken by palladium, and now this you get the enol which will be coordinated with palladium, and after that reductive elimination will give you ketone and palladium 0, ketone, HCl, water. So, this is reductive elimination happening, and this enol. So, enol we know that enol after tautomerization goes to the ketone, that is the ketoenol tautomerization, and in this process you get HCl, water also, and this palladium 0 will be reoxidized to palladium chloride. So, there is a mistake here, this will be CuCl2 and this will be CuCl. So, this is CuCl, that CuCl with oxygen HCl is converted to CuCl2, and that CuCl2 is oxidizing palladium 0 to palladium chloride and itself getting reduced to CuCl. So, this CuCl, that is the role of oxygen to oxidize CuCl to CuCl2, and palladium is getting oxidized to palladium chloride by CuCl2. So, this is the overall mechanism of this reaction, and the important for regioselectivity is the Markovnikov addition that we will see. Sometimes the anti-Markovnikov product also can be obtained. So, some examples, suppose if you take the secondary alcohol with an allyl group, that is the terminal olefin, and under this condition palladium chloride 10 mole %, chromium trioxide, that is the oxidant here instead of copper chloride, and acetonitrile water 7:1, 60 degree centigrade 8 to 18 hours. Of course, this should be under oxygen atmosphere or in presence of air, and after that you treat with concentrated HCl. So, what happens? You get first this one, beta hydroxyketone, and beta hydroxyketone if you treat with HCl, then water gets eliminated and you get this alpha beta unsaturated ketone. Second step is the dehydration reaction. So, this is also the same mechanism, the Markovnikov addition is happening. This was published in JOC 2016. Now, if you treat an alkyne, alkyne also under this condition goes to diketone. Suppose 5 mole % palladium bromide, 10 mole % copper bromide, 1 atmosphere oxygen, 60 degree centigrade dioxide water, you get this diketone up to 97%. So, this is also an important reaction to convert alkynes to diketones. This was published in Organic Letters 2009. Now, we will discuss chemoselectivity. Suppose if a substrate has 2 olefins, now which olefin will get oxidized or which olefin will react in the Walker process, that we will see, and there the steric hindrance is playing a role. Suppose if you think about this substrate, here an terminal olefin and this is internal olefin. So, this is internal olefin and this is terminal olefin. So, the internal olefin is steric hindrance is there. So, the terminal olefin is only reacting under this condition, palladium acetate 5 mole %, this molybdenum catalyst 1 mole %, oxygen, sodium chloride 5 mole %, ethanol water. You get this one and this double bond is untouched. So, this is very important that regioselectively you can get this product in 97% yield. Here also no isomerization and no over oxidation. Now, if you think that both are terminal olefin, and in this case this olefin is close to the substituent, on the other hand this olefin is quite far, this double bond is quite far from the substituent, and when you put palladium chloride 40 mole %, copper chloride 1 equivalent, oxygen only 3 hours if you get, then this ketone is formed, this double bond is untouched. So, this is very important, which is sterically less hindered, that is getting oxidized. Now, if you put the reaction for more time like 33 hours, then you get this diketone, both double bond getting oxidized to the carbonyl group, and you get this 71% yield. So, if you start for shorter time, then you can get the selective oxidation. On the other hand, for longer time you get the diketone. Also, if you see here also both terminal olefin and here also this olefin is close to this methoxy substituent, just methoxy also can give a selectivity. So, this is very sensitive reaction, and with this terminal olefin is quite far. So, you can see when Walker oxidation room temperature, under this standard condition room temperature, you get only this ketone. So, that double bond which is far from the methoxy is getting reacting, and you get this ketone with having the double bond. Now, if you do the reaction at 50 degree centigrade, then you can get this diketone. So, higher temperature is required for the reaction of the sterically hindered olefin. So, either you need longer time or you need high temperature for the diketone synthesis. This was published in Synthesis 1984. Also, we will see the chemoselectivity compatibility with functional groups. Like this substrate, if you see there is a terminal olefin and aldehyde motif is there, and with this condition palladium chloride 10 mole %, copper acetate 20 mole %, AC-N-2, this is solvent NN dimethyl acetamide, water 7:1, oxygen in atmosphere, room temperature 30 hours, you get this ketoaldehyde, and this aldehyde group is untouched under this condition. Also some isomeric carbonyl compounds in 3 to 10% yield, and this product is obtained 62% yield. This work was published in Tetrahedron later. So, aldehyde, we know that this is very prone to oxidation, that did not react under this condition. Also, if you see this compound, there are many chiral center is there, sulfoxide, diol and a fluorine, and this is the terminal olefin, and with palladium chloride 20 mole %, copper chloride 1 equivalent, oxygen atmosphere, DME, room temperature overnight, you get this ketone first. And what happens, this ketone in situ reacts with the diol, because you can see nicely 6-membered ring will form here, and this is another 5-member ring. So, this ketal is formed, because these two oxygen OH is reacting with the carbonyl group, and you get this ketal in 80% yield. Also, if you see this compound, there is also chiral center here, also this is a stereogenic center, and under this condition palladium chloride 10 mole %, copper chloride 1 equivalent, DMF water 6:1, oxygen atmosphere, room temperature condition, you get this ketone, and these groups are untouched or not disturbed in this process. And PHF is a protecting group. Here you can see the structure of PHF, that is the amine was protected, and this product is obtained in 80% yield, and this work was published in JOC 2004. So, we can see that defined functional group also can be tolerated in the Walker oxidation process. Now, we will see anti-Markovnikov oxidation. So far we have seen that the Markovnikov addition happens, and if you have a terminal olefin you get the ketone. Now, we will see if you have a terminal olefin via anti-Markovnikov addition you get an aldehyde. Like this is the olefin, this is the Markovnikov product, the ketone normal, that whatever seen. Now, in the abnormal cases you can get the aldehyde, that means the water attacks here, and this is the anti-Markovnikov, and few examples are known. So, what happens in the normal cases, whatever we have seen, that this kind of carbocation intermediate will form, and more stabilized carbocation, that is the more substituted, that is here, that is the Markovnikov addition, and water will attack to the more substituted carbon atom, that is why you get the Markovnikov product. And this is the stability of carbocation. We know that tertiary is more stable than secondary, secondary is more stable than primary. Now, in the anti-Markovnikov cases, what will happen? So, anti-Markovnikov cases, one possibility will be that the nucleophile might face the steric hindrance, because this is the more substituted more substituted carbon atom, there the steric effect might be there. If the neighboring groups are bulky, then this nucleophile may not attack this center. Instead, it can attack to the terminal carbon, because there also might be little delta plus, because it is also coordinated with palladium. Another thing, the reverse polarity, that also might be possible. Suppose if you generate a terminal carbocation which is stabilized by other olefin or other groups, the other groups might stabilize this carbocation. So, that we also will see, and that case you can get also anti-Markovnikov product. So, we will see now anti-Markovnikov Walker oxidation proximal complexing function. So, substrate giving product with this standard condition, palladium chloride 10 mole %, copper chloride 1 equivalent, DMF water 7:1, room temperature, oxygen. And now, if you see this substrate, this is syn diol and a terminal olefin is there. Now, if you put under standard condition, you get 90% yield of this ketone, and that is the Markovnikov addition. Now, if you put this diol protection, so this is called acetonide protection, that is the reaction with acetone. If you do, then this diol will be protected, and once it is protected, the aldehyde is formed, that is the anti-Markovnikov product, and this is obtained 93% yield. So, what happens after the protection, this carbon atom feeling steric effect, and that is why the nucleophile cannot attack. So, water cannot attack to this, and instead it is attacking to this terminal carbon atom. Not only this syn, this is the trans, so this is syn, this is trans. Trans cases also you get anti-Markovnikov product, though yield got reduced to 83%, but here selectivity is good, that is the terminal carbon atom is reacting with the water and you get the aldehyde. Also, if you have a anhydride, so this is anhydride, this diol is protected anhydride, in this case also the aldehyde is formed. So, what happened? The aldehyde is formed and this anhydride may be getting hydrolyzed, and what happened? The aldehyde whatever is formed, that is eliminating water, and you get this alpha beta unsaturated aldehyde. So, this is very important, that whenever you have a steric effect at the internal carbon, then the terminal carbon atom will react, and this was published in JOC 1995. And this is also an diene. If you see this one, now we will see the proximal complexing function. So, if you see this diene, this is actually 1, 2, 3, 4, 5, 1, 5 diene, and there is a quaternary center here, and this is the methyl substitution. And interestingly, with palladium chloride 50 mole %, copper chloride 1 equivalent, DMF, water, oxygen, atmosphere, you get the anti-Markovnikov product in 99% yield. So, this double bond is only reacting, this double bond is not reacting, and this bond also is reacting at the terminal carbon. So, this is quite interesting what is happening. Now, if you see the mechanism, proposed mechanism, that this bond, double bond will react with palladium because there is a methyl substitution. So, this will be less sterically hindered, and now this carbocation will be stabilized by this pi electron cloud. So, the pi electron cloud of the olefin is stabilizing this carbocation, and that is why this is called non-classical carbocation is formed like this. The electron cloud will delocalize here, and now water attacks to this center and you get this intermediate, and after elimination of course you get the beta hydride elimination, you get the aldehyde. So, we will see some more examples. Suppose if you see this diene, here also quaternary center is present, and this is the exocyclic olefin, and this olefin is little bit far, and this olefin is reacting in anti-Markovnikov fashion, because here also this carbocation will be stabilized by this double bond. Now, interestingly, if you put two methyl groups here, what happens? This substrate. Now, this double bond will face some steric repulsion, because there is a methyl group here. So, the nucleophile will not attack to this double bond. Instead, it will react to this exocyclic olefin, and here also the terminal carbon atom will react, because here also the non-classical carbocation will form, and you get the anti-Markovnikov product. So, both cases you get Markovnikov product, that is the aldehyde is forming, but one case this double bond is reacting and another case this double bond is reacting. So, this is very important, the steric effect is playing a very role, and if there is a non-classical carbocation formation, if there is another olefin which can stabilize that carbocation, then you can get this anti-Markovnikov product, and this work was published in Tetraeder Letter 2003. Now, we will see a different reaction which is Suji-Trost reaction, also called the Trost allylic alkylation or allylic alkylation. It is a palladium catalyzed substitution reaction involving a substrate that contains a Levig group in the allylic position. The palladium catalyst first coordinates with the allyl group and then undergoes oxidative addition, forming the pi allyl complex. So, this is very important, and this pi allyl complex, that is electrophilic. So, different nucleophile can react. This allyl complex can then be attacked by a nucleophile, resulting in the substituted product. This work was first pioneered by Giro Tsuji and later adapted by Barry Trost in 1973 with the introduction of phosphine ligands. The introduction of phosphine ligands led to the improved reactivity and numerous asymmetric allylic alkylation strategies. So, this is the overall reaction. If you have this allylic substitution X here, which is Levig group, and when you put the palladium catalyst, then this pi allyl palladium complex is formed, and this X comes to palladium, and now nucleophile comes and you get this product, and you can see here the nucleophile attacks at the terminal carbon atom. So, this is very important, and also the olefin is regenerated. So, X is Levig group, Nu is nucleophile, and now different kind of nucleophile can be used: malonate, primary alcohol, carboxylate, phenol, alkylamine, azide, etc. X is equal to OCOR, OCOR, OPOR2, Cl, etc. So, different nucleophile and different Levig group can be put, and this was a chemical reviews 1996. So, they are the scientists who developed this reaction. This is Japanese scientist Tsuji, and this is American scientist Barry Trost. Now, we will discuss the mechanism of this reaction. So, you can use palladium 0 or palladium 2 precursors, and now this palladium 0 will do a coordination with this double bond first, and after that the oxidative addition will take place, and this bond will of course break, and the X will come to the palladium, and there might be ligand exchange also, that ligand can remove this X to get this one. So, overall a pi allyl palladium intermediate is formed, and as I have told that this is electrophilic. So, a nucleophile can react, and nucleophile reacts such that you get this nucleophile attack from the terminal carbon, and you get this intermediate, which after reductive elimination you get your olefin, and palladium 2 becomes palladium 0 here. So, this is the reductive elimination. Now, we will see that if you have chiral compound, then with soft nucleophiles you can get retention, and hard nucleophiles you will get inversion. So, this is very interesting what is happening. So, if you have this substrate, then this palladium ligand interacts, coordinates, and then this pi allyl palladium is formed. So, this is pi allyl palladium. And what happens in case of soft, if it is soft, then this does not want to interact with palladium. So, what happens? It wants to stay away with palladium. So, it reacts from the side where the palladium is present. So, it ultimately it is reacting with the same side where X was there. So, that is why it is reacting opposite of the palladium, that is the same side of X, and you get this one. And after reductive elimination you get this, and this is the product, and ultimately the retention of configuration happens. Now, in the hard nucleophile you get inversion. So, what is happening here? Here also the coordination, and then the pi allyl palladium is forming, pi allyl palladium. Now, because this hard, so hard means this is also strong. So, strong nucleophile that wants to interact with the palladium, because palladium is a charge, positive charge is there. So, that wants to interact with palladium. So, ultimately what happens? It came from the same side of palladium. So, same side, and that is why ultimately it is opposite side of X. So, ultimately you get an inversion. So, this product is formed where the nucleophile is coming from the same side of palladium, ultimately you get an inversion, as the inversion of configuration happens. So, this kind of reaction we will see by examples with soft nucleophile. Suppose this chiral substrate if you use, and with JD, this is the scene actually, scene is more 98:2, and we react with this malonate with tetrakis triphenyl phosphine palladium, you get 90% yield of this product. And if you see, it is coming from the same phase of acetate. So, this is retention, and you get this product in 98:2. Now, if you react with this one EZ, that is the trans one, and where O acetate is down now with 93:7 ratio, and same malonate if you use and same condition, you get little less yield, 80% yield, but the stereochemistry is opposite now whatever earlier products with this one. So, here also retention is happening. So, independent of whatever the other stereochemistry is not affecting, it is the acetate stereochemistry, that is the pi allyl palladium intermediate, and there the reaction that is very important for the retention of this stereochemistry. Asymmetric catalytic Sooji-Strauss type reaction is possible. Suppose here this is secondary acetate and this is malonate with this ligand. You can see this there is a phosphine and amino group is there with palladium acetate ligand, because this phosphine nitrogen will bind with palladium, and THF solvent you get this product. The malonate group comes at the same carbon where the acetate was there, and you get 95% yield and 96% E. Though this pi allyl palladium will be symmetric, so it does not matter it reacts with which carbon, because it will be symmetric, but you get high yield and high E. This was published in Tetrahedron Asymmetry. Not only malonate, you can use some acetate motif also, and with this ligand. So, there is a mistake, this should be down. So, this is actually C2 symmetric. So, this is chiral ligand C2 symmetric. If you make a trans here, then it will be C2 symmetric, and if you react with this acetate 7 member ring allylic acetate, and if you react with this, then you get this product. So, this acetate only methyl is going to ethyl, but almost same thing. So, that is why this is called deracemization reaction, deracemization of allyl acetate. So, this is very important. You react with this catalyst ligand, THAB is the additive tetrahexyl ammonia bromide dichloromethane solvent, you get 91% yield. So, very efficient, and 98% enhanced selectivity. So, a racemic is converting to a chiral compound with this ligand and palladium catalyst. So, this is reported by Barry and Trost in JACS 1994. Palladium catalase coupling chemistry. So, now we will discuss different palladium catalase coupling. So, Suzuki Miura, that we have already discussed when boronic acid. If you use the tin, then stellate, this also we have already discussed. Negecy, if you use zinc, then you get the Negecy. So, this we will discuss today. RMGS Grignard, then it will be Kumada, this also we will discuss. RSI3 Hiyama, this we will not discuss. Triple bond alkyne, if you use, then Sonogosira, this also we will discuss. And olefin, if you get react, then you get substituted olefin, this is Hague reaction we will discuss. Amination, this is Buchwald-Hartwig amination we will discuss. If you use the cyanation formation, that is the cyanide we will not discuss, and this we will discuss. Carbon monoxide nucleophile carbonylative reaction we will discuss. So, first we will discuss Hague reaction, and the Hague reaction also called the Mizoroki-Hague reaction. It is the chemical reaction of an unsaturated aldehyde or triplet with an alkene in the presence of a base and a palladium catalyst or palladium nanomaterial based catalyst to form a substituted alkene. So, an alkene is converting to a substituted alkene, and it is now named after T. Mizoroki and Richard F. Hague. Hague was awarded the 2010 Nobel Prize in Chemistry, which is shared with Negecy and Suzuki, of course, for the discovery and development of this reaction. So, Hague first developed this reaction, that is why it is called Hague coupling. This reaction was first example of carbon-carbon bond forming reaction that followed a palladium 0 palladium to catalytic cycle. So, this is very important. The same catalytic cycle that is seen in other palladium 0 catalyzed cross coupling reaction. The Hague reaction is a way to substitute alkenes. So, this is the reaction. Suppose if you have a aryl halide, if you have a olefin with palladium 0, phosphine, triethylamine base, you can get two olefin products. One is the normal, another is the isomerized. So, two olefins can be formed, but we will see the regioselectivity issues. And if you have a vinyl halide and an olefin, then you can get conjugated diene. That also is possible with Hague coupling reaction. So, this is the account of chemical research, full story is there, 1979. So, what could be the mechanism? So, here also the palladium first reacts with the aryl halide, and this is the oxidative addition, and now your olefin will interact with this palladium, because this is palladium charge now. So, the olefin will do a coordination, and this is very important, alpha beta migrator insertion will happen. So, now this one will add to the double bond, and this is also very important. We will see the regioselectivity issue later, but first what we want to see, this aryl and palladium X, it is coming from the same side. So, this is syn addition. So, this is very important, syn addition is happening. So, this it is from the same side. Now, what will happen? You have to give a rotation, because if you want to take an hydride, it should be from the same side of palladium. So, if you give a rotation, then the phenyl will be down and one hydrogen will be the same side of palladium. So, this is rotation. And after that rotation, only the elimination, beta hydride elimination will happen. So, like this hydride will be taken by palladium, and you get this olefin, and this is formed, which after reductive elimination is from the HX and Ln palladium 0, and this palladium 0 again react in the with the aryl halide. So, this is the overall reaction. If you see these two things very important, syn addition and syn elimination, that we will see. So, what is the evidence that how do we prove that alpha beta migrator insertion and the syn beta hydride elimination is happening? So, if you put this methyl cinnamate with this deuterated bromobenzene, now this is trans orientation. After this coupling, palladium 0 tert-butyl phosphine, this is the amine dioxane solvent. You see now in the product this phenyl and CO2Me are on the same sides. So, this is single isomer is forming. So, what could be the mechanism? And this is a proof that the addition seal elimination will happen. So, first if you see this cinnamate, we can draw like this also, this meaning the trans is there, phenyl is this and this is down. So, this is trans. Now, syn carbopalladation will happen and like this palladium is going here reacting, you get this, and here now you have to give a rotation because palladium in the same side of this. So, a hydride has to bring to the same side, that is why you have to give rotation. And now, if you give the rotation, then what happens? The pH comes from the same side of CO2Me. And after the elimination, you get this. So, the pH and CO2Me is same side after beta hydride elimination. Beta hydride elimination and reductive elimination, of course, you get the palladium 0 and this is the product. Also, if the R group has no hydride for syn elimination, then a beta hydride may be abstracted elsewhere. If you want to generate a olefin, of course, you need a hydride, and that beta hydride should be brought into position for syn elimination with the palladium. Suppose if you react iodobenzene with cyclohexene with this condition palladium acetate triethylamine, then you get this one. And you can see for cyclic structure we cannot give rotation like earlier we have given. So, what happens? This phenyl and this palladium is on the top side on the same face. So, this hydride cannot bring to the same side. So, what happens? There is a neighboring carbon where the hydride one hydrogen of course is the same side. So, you get this olefin. So, olefin is now not with this conjugated. So, this is racemic, of course, you get this product. So, not this conjugated product, not here where the original. So, what happened? Double bond changes its place. So, double bond changes its place for cyclic system or cyclic olefins. And this tells that the syn elimination is very important. Now, we will see regioselectivity issue. Of course, this is a nucleophile kind of thing, and if you have a electron with a substituted, then the reaction will happen here, the aryl will be here and you get this product. On the other hand, if a electron donating group is present on the olefin, then the AR will come on the same carbon where the electron donating group is present. Reactivity, monosubstituted olefin will react, then the disubstituted olefin, then this is 1,1 disubstituted, this is 1,2 disubstituted, this is cis, this is trans, and then trisubstituted. So, steric repulsion or steric effect will control the regioselectivity issue. Now, good additives. So, suppose this is the standard reaction, you can get two products, and palladium, it can be Pd2 dBA whole 3. So, this is also palladium 0 dBA whole 3. So, this is the dBA pH, this is dBA. Also, palladium acetate can be used, this is palladium 2 and palladium 0, triphenyl phosphine palladium. Ligands, triphenyl phosphine, tert-butyl phosphine, 1:1, palladium phosphine. Solvents, dioxane, DMF, acetonitrile, base, triethylamine, cesium carbonate, inorganic base can also be used, and this is dicyclohexyl methylamine. So, now we will discuss intramolecular Heck reaction. So far whatever we have discussed intermolecular, now intramolecular, if the vinyl halide or vinyl triplet and the olefin in the same molecule to couple, then you can get a ring. And now, depending on endo and exocyclic cyclization, you can get two different rings, of course. Now, what is the selectivity rule? Rule of thumb is that if you generate a 5-member ring, that formation will be faster than 6, that will be faster than 7, also 5 will be faster than 3, 4. And endocyclization is less likely for rings less than 6 carbon. For larger rings, only endocyclization is possible. So, for higher than 6 or 6 cyclization, the endo is possible, otherwise you have to make exocyclization. So, some examples we will see. So, if you see this substrate, here the vinyl triplet is there, here is a olefin is present, here is a olefin is present, and if you count here, this carbon if you consider 1, 2, 3, 4, 5, 6, now 6 exocyclization will happen with this catalytic system, triethylamine, and you get this one. Now, if you see this intermediate, here no beta hydride is present, because this is now quaternary. So, again it will cyclize. Now, if you see this is 1, 2, 3, 4, 5. So, again 5 exocyclization will happen, you get this intermediate, because 5-member ring is from here. And now, if you see this one, there is a beta hydride to eliminate, and that will eliminate to give a olefin. So, this will be the ultimate product. So, this is tandem cyclization. Also, if you see this one, intramolecular version, this is a triplet, aryl triplet, here is a olefin substituted is present. Now, if you see the count 1, 2, 3, 4, 5, 6, so this is also 6 exo is possible, 6 exo. Also, the stereochemistry is a effect, because this is a stereogenic, and the addition will make a stereogenic center, and this stereochemistry will be cis, because the double bond attaches from the bottom. So, because this one is, if you think it is in the bottom, then it will attack from the bottom also. So, it does not want to change its side. So, it will be the syn orientation. Now, your palladium is here now, but if you see this is quaternary carbon. So, hydride is present in the neighboring carbons, and it is always like cyclic system. Here the elimination will happen, and you get the double bond here, and this is the product. This is syn. The stereochemistry is syn. This was published in Tetrahedra 1994. If you see this substrate, there are many triple bond and double bond is present. This is the vinyl iodide, and if you see this triple bond, this is 1, 2, 3, 4, 5, but you need a 5 endo, which is not possible. But if you see this carbon 1, 2, 3, 4, 5, 6, so 6 exo is possible. So, 6 exo favored than 5 endo, and with this palladium 0 triphenyl phosphine triethylamine, you get first this intermediate, your palladium is now here. Now, again if you see, this is 1, 2, 3, 4, 5, 6. So, this 6 exo again is possible. So, after 6 exo, this carbon, they are now palladium. Again we will do cyclization 1, 2, 3, 4, 5, 6. Though there is a hydrogen here, but it will further cyclize, because the alene will form, but that process will be slower compared to 6 exo cyclization. So, 6 exo cyclization will happen, this one will form, but here also the beta hydride is not available, beta hydride not available. So, what will happen? This again will cyclize. So, 1, 2, 3, 4, 5. So, again 5 exo. So, 5 exo you get this one, this intermediate. And if you see this intermediate, there is a hydride, of course, here this carbon, and syn beta hydride elimination, if you get this product. So, this is very important. If you have a substrate with many double bond and triple bonds, then depending on the 6 exo, that is the Baldwin rule, 6 exo, 5 exo, many cyclization is possible, and you get a polycyclic product. So, this is polycyclic product. Now, we will discuss Negishi coupling. So, Negishi coupling utilizes organozinc reagents as starting material to cross couple with organohalides and equivalents. This method is compatible with a good range of functional groups on the organohalide including ketones, esters, amines and nitriles. The organozinc reagent can be prepared in situ by a variety of methodologies such as transmetallation of the corresponding organolithium or Gigner reagent or via oxidative addition of activated zinc to a organohalide. So, this is the overall reaction and halide and then the zinc compound palladium catalyst, you get this cross coupled product. So, what is the mechanism? Here also the oxidative addition will happen first with the aryl or vinyl halide to get this. Now, the transmetallation will happen. So, this is a nucleophile R1 that will make a substitution here. So, X will be eliminated and X will react with zinc now. So, zinc X dash X is formed and your R1 is with palladium now. So, this process is called transmetallation, and after the reacting elimination you get the coupled product RR1 and you get the palladium 0. So, R can be, that is the halide, can be aryl, alkenyl, propargyl, acyl. R1 that is the zinc one, this can be aryl, alkenyl, allyl, benzyl, homoallyl, homopropargyl, etc. So, broad range. X can be defined iodo, triplet acetate, X dash also iodobromochlorine and L is ligand. So, one part Negishi cross coupling reactions of in situ generated zinc reagents with aryl chloride, bromides and triplets we will see now. So, this is the in situ generation with zinc, lithium chloride, THF, you get this zinc complex, and now react with aryl halide, PEPC. PEPC is a N-heterocyclic carbene, palladium is there, that is the catalyst now. THF solvent in 25 to 50 degree centigrade, you get this cross coupled product in 67 to 97% yield, and this was reported in JOC 2008. Nickel catalyzed asymmetric Negishi cross coupling of secondary allylic chlorides with alkyl zincs. So, this is the reaction. This was developed by Fu, I think, Fu group, GC Fu. So, if you have a secondary allylic chloride which is racemic, and now if you have a zinc bromide 1. RZnBr 1.2 equivalent 5 mole % of nickel chloride lime, and this C2 symmetric pi box. So, this is C2 symmetric, this is the pi box, this coordinates with nickel, and this cross coupled product you get in very high yield as well as the enantiomeric excesses. This work was published in JACS 2008. Now, we will discuss Kumada coupling. So, the cross coupling of organohalides with Gigner reagents is known as the Kumada coupling. Although it suffers from a limited tolerance of different functional groups, the higher reactivity and basicity of the Gigner reagent allows viable reactions to take place under mild conditions. So, this is very important. Gigner can do many side reactions, but it is also high reactive. So, if you have a aryl or vinyl halide, then the Gigner with palladium 0, you get the cross coupled product. And we will see now examples pseudo-retentive palladium catalyzed Kumada Koryu coupling of alkenyl halides at room temperature. So, this is an example, the in situ generation of the Gignard from the iodobromobenzene with this one, if you put then, or magnesium, then the Gigner reagent is formed. And now, if you react with vinyl halide or vinyl triplet with palladium catalyst, this is the base, then you get the cross coupled product. So, this is the product, and you get this product in high yield. This was published in Organic Letters 2014. Now, we will discuss the mechanism. The mechanism is same like Negishi coupling. Here also the oxidative addition will happen, and the transmetallation. Earlier we have seen zinc, Negishi, but Kumada coupling, this is the magnesium, Gignard. Now, transmetallation will happen, R dash is nucleophile, will reacts with the palladium, and this is the byproduct. Now, trans isomerization will have to happen, so they will be close to each other. After that, reductive elimination, you give this product and you get your palladium 0. So, some examples: Kumada-Koryu reaction of alkyl halides with alkynyl nucleophiles. This is the alkynyl Grignard or lithium reagent, and with R-Y, R- is here alkyl, and 2.5 mole percent of Pd2DBA3, 10 mole percent of triphenyl phosphine THF 65 degree centigrade, you get this internal alkyne or substitution. So, substituted alkyne is formed. This was published in Organic Letters 2004. Interestingly, if you have a Grignard reagent with a tertiary carbon atom, that case also the reaction will happen. This is nickel catalyzed Kumada cross coupling reactions of tertiary alkyl magnesium halides and aryl bromides or triplets. And for that you have to use nickel catalyst and this imidazolium salt. So, this is 18 the number here, imidazolium salt, and minus 10 degree in 90 minutes you get this cross coupled product in good yield. So, R can be Cy here in this catalyst and X is equal to BF4. So, JAX 2011 133, it was 8478, this was published. Now, we will discuss Sonogo-Shira coupling. So, Sonogo-Shira coupling, in this process you generate alkyne. So, we have seen that Kumada coupling also alkyne and Grignard you can get the triple one, but simple alkyne you can use in Sonogo-Shira reaction. Sonogo-Shira reaction is a cross coupling reaction used in organic synthesis to form carbon-carbon bonds. It employs a palladium catalyst as well as copper co-catalyst to form a carbon-carbon bond between a terminal alkyne and an aryl or vinyl halide. And the Sonogo-Shira cross coupling reaction has been employed in a wide variety of areas due to its usefulness in the formation of carbon-carbon bonds. The reaction can be carried out under mild conditions such as room temperature in aqueous media with a mild base, which has allowed for the use of Sonogo-Shira cross coupling reaction in the synthesis of complex molecules. So, this reaction is very important and its applications include pharmaceuticals, natural products, organic materials and nanomaterials. So, this is the reaction. You can use an aryl halide or vinyl halide and then an alkyne. So, this is very important, generally the terminal alkyne. So, terminal alkyne if you use, then if you get substituted alkyne. This is a Sonogo-Shira reaction and you need palladium catalyst as well as a copper catalyst. Copper is required to activate the triple this hydrogen it will take. So, the copper acetaldehyde will form and base is required. So, what is the mechanism? So, this is the mechanism as I told, the copper react with the triple bond alkyne, first the coordination and then the copper acetaldehyde. So, this is copper acetaldehyde is formed with base takes of the HX and this one react with this one after oxidative addition. So, this is the transmetallation. Earlier we have seen zinc, magnesium, now we will see copper. So, this is a nucleophile, this attacks to the palladium now and you get this one after reductive elimination you get the alkyne, that is the cross coupled product and the palladium you get, which will react again under oxidative addition. So, two catalytic cycles are present, one is copper cycle, another is palladium cycle. So, copper main role is the to make the copper acetaldehyde from alkyne. Now, we will discuss Buchwald-Hartwig coupling. Palladium catalysis has also been expanded in the formation of carbon nitrogen bonds. In 1995, Buchwald and Hartwig independently reported the palladium catalyzed coupling of aryl halides with amine nucleophiles in the presence of stoichiometric amount of base. So, this is the reaction Rx, this is secondary amine, you get a tertiary amine product. And this is an example, if you use chlorobenzene and a secondary amine with this catalyst. So, here palladium phosphine is present and sodium tertiary butoxide or sodium methoxide base, then you get this tertiary amine and this work was published in Organic Letters 2003. So, what is the mechanism? The mechanism is same, that the oxidative addition will happen like palladium catalyzed coupling reaction. So, this is the oxidative addition oxidative addition is happening like earlier, this can be like this also, and now the amine comes. So, addition to of the amine to the oxidative addition complex. So, this addition is happening here. So, amine is nucleophile, it is reacting to the palladium, and now this HX will eliminate. So, if you base, then the base HX will eliminate and you get this intermediate, and after that you get a reductive elimination of this. So, the amine is reacting with aryl group, reductive elimination will give you the amine and your catalyst back. So, this is the overall reaction. Now, we will discuss palladium catalyzed carbonylation reaction. So, carbon monoxide can also be incorporated in the palladium catalysis and defined nucleophiles can be used. So, the amide esters can be obtained. Palladium catalyzed carbonylation is compatible with a range of functional groups. This gives it significant advantage over standard organolithium and Grignard chemistry for the synthesis of aryl halides, acid esters, amides. So, this is the reaction Rx with palladium 0, carbon monoxide, nucleophile and base, you get this carbonyl compound, and depending on the nucleophile you get defined carbonyl compounds like OR dash, that is ester. If you have a amine, then you get a amide, and if you give H minus, then what will happen? Aldehyde. So, aldehyde will form if there is a H minus, that example we will see. Suppose if you have this one, this bromobenzene and this substituent is present with this catalyst PDCl to DPPP and with carbon monoxide 3 bar, this is the hydride source triethylsilane and this is the base sodium carbonate DMF 90 degree centigrade. This bromine is displaced with aldehyde moiety. So, now this COH is there. So, carbonyl is coming from the carbon monoxide, this hydride is coming from HSiEt3. So, this is another example like here thalidomide with substituent is there and there the amine is the nucleophile and carbon monoxide of course is present with ligand triphenyl phosphine Db is the base, then you get the amide. So, this is the amide. So, what is the mechanism? So, mechanism is same, the oxidative addition happens here as you have seen oxidative addition, and now carbon monoxide will attack to this one. Carbon monoxide actually inserts this bond, palladium carbon bond, and carbon monoxide is present here now. Now, a nucleophile will react to this activated intermediate like this, your palladium will eliminate to generate this, and of course, you get your product here. This is product and this is the catalyst become like this. Now, with base HX will take up and your palladium catalyst is regenerated. So, this is the overall reaction and this publication JOC 1996. So, this is very important, depending on the nucleophile you get defined carbonyl compound like amide, esters, aldehyde. Now, we will discuss another oxidation, Segusa-Ito oxidation. This is process is for the conversion of saturated carbonyl to unsaturated carbonyl. So, it was discovered in 1978 by Takeo Segusa and Yoshihiko Ito as a method to introduce alpha beta unsaturation in carbonyl compounds. The reaction as originally reported involved formation of a sterile enol ether followed by treatment with palladium acetate and benzoquinone to yield the corresponding enone. So, this is important that cuprate first add to the 1,4 addition followed by enol silane formation to get this enol silane. And now, if you put palladium acetate 0.5 equivalent and this is oxidant 0.5 equivalent parabenzoquinone, then you get the enone. So, mechanism is that the palladium acetate reacts first coordination, and remember here palladium is 2 is present, and after that here 2 acetate are there. One acetate will eliminate like TMAO acetate, here now 1 acetate. Now, this oxygen will coordinate with palladium. First the oxo-allyl palladium complex will form. So, first this one will be equilibrium with this one. So, this is called the oxo-allyl palladium. Oxo-allyl palladium. So, in the oxo-allyl palladium this palladium is interacting with this oxoallyl species. Now, what will happen? This palladium will see the neighboring hydride also. So, what happens? The beta hydride elimination will happen, beta hydride elimination. And what happens after beta hydride elimination? Of course, you get a double bond, and now your hydride is with the palladium, and a double bond is generated, of course, which after reductive elimination it generates reductive elimination yields the product along with acetic acid and palladium 0. It has been shown that the product can form a stable palladium 0 olefin complex, which may be responsible for the difficulty with reoxidation seen in catalytic variants of the reaction. That is why stoichiometric amount of palladium is used generally, and this was published in JOC 1978. So, we will see some examples. Here suppose saturated ketone is there, 6-member ring, and many this is a complex structure, many functional groups are present. Here is a carbamate motif is there, and under this condition first you have to make an enol silane with LHMDS, TMS chloride, THF 0 degree centigrade. So, you make an enol silane and then you put palladium acetate, acetonite at room temperature, you get the enone in high yield. This was published in Organic Letters. Also, if you see this structure, here also a carbonyl compound is there. Similarly, LDA TMS chloride, you generate the enol silane, then palladium acetate, sodium carbonate, acetonitride, you get this enone. Because this hydride elimination will be difficult, that is why the less substituted carbon atom, there the hydride delivery is happening. This was published in Organic Letters 2006, and this is a larger ring. Here the alcohol you have to oxidize with PCC to generate the aldehyde, and the aldehyde then you make a enol silane with TMSO triplet triethylamine, and with palladium acetate acetonitride you get the alpha beta unsaturated aldehyde. So, this is called enol. So, enols as well as the enones can be generated from the Segusa oxidation method. This was published in JACS 1988. So, today whatever we have seen, first the Walker process we have seen. The Walker process, a terminal olefin generally converting to ketone or aldehyde. Ketones are forming when that is the normal product via Markovnikov pathway. On the other hand, aldehyde can be formed when there is a steric effect at the substituted carbon atom, or there is a non-classical carbocation formation. We have seen that the olefin, external olefin is stabilizing the carbocation, then you can get anti-Markovnikov product. Then we have seen the Sujit-Trost allylation. Here the allyl X, where X is a leaving group and nucleophile can be soft nucleophile as well as the hard nucleophile. So, soft nucleophile we have seen the retention of stereochemistry, and hard nucleophile the inversion of stereochemistry. Also asymmetric versions are possible with chiral ligands. Then we have discussed different cross coupling reaction, Heck cross coupling. Here the syn addition and syn elimination is very important. So, cyclic systems, cyclic olefin, the double bond has to isomerize, that we have seen. And then we have seen the Negishi coupling. Here the zinc are used, and Kumada coupling, the Gignards are used. So, Gignard, the alkynyl Gignard can be used for the generation of substituted alkynes. And Sonokushira coupling we have seen, there the alkynes can be used, terminal alkynes, and palladium copper co-catalyst method, 2 catalytic cycles are there to generate the substituted alkyne. Then we have seen Backwall-Hartwig amination. Here the amine has to be used and you get the aminated product. Then we have seen the carbonylative reaction. Here carbon monoxide is used, and with external nucleophile, depending on the external nucleophile you can get ester amide as well as aldehyde. And lastly, we have seen Segusa oxidation. It converts saturated carbonyl to unsaturated carbonyl via enol silane, and stoichiometric amount of palladium acetate is used. And this method we have seen that can generate also enol, that is the alpha beta unsaturated aldehyde as well. Thank you.